Hi, welcome back to my channel. My name is Gina. A few weeks ago, I introduced the 3 types of elementary row operations. Now in this video, let's look at how to use the elementary row operations and reduce a matrix into reduced row-echelon form. Let's start with the definition. What is a reduced row-echelon form? A matrix is said to be a reduced row-echelon form if the following 3 are all true. First condition is if there's any 0 rows, they have to be at the bottom of the matrix. Second condition is that for each non-zero row, the leading entry or the pivot is 1. And all the other entries in the column where there's a leading entry are 0. The third condition is that the leading entry in each row is to the right of the leading entry of any row above it. So if there are any leading entries, they have to be from the top left to the lower right. Let's look at this example. Let's identify whether these 5 matrices are in reduced row-echelon form. Matrix A, 1, 0, and 0, 3. Let's go through the 3 conditions one by one. First condition is if there's any 0 row, they have to be at the bottom. But for this matrix, it does not have 0 row, so first condition is met. Second condition is that each leading entry has to be 1. But the second row of matrix A, the leading entry is 3. It is not 1. So matrix A is not in reduced row-echelon form. Now let's look at matrix B. Again, we are going to go through the 3 conditions. First, is there any 0 rows? No, in matrix B, there's no 0 rows. So first condition is met. Second condition, for each non-zero row, the leading entry is 1. In the first row, the leading entry is 1. In the second row, the leading entry is also 1. And the second half of the second condition says all other entries in the column where there's a leading entry are 0. Let's look at the first column. Other than the leading entry, the other entry is 0. And the second column, the only non-zero number is the leading entry. So the second condition is met. How about the third condition? The leading entry in each row is to the right of the leading entry in any row above. This is also true since the leading entry of the second row is to the right of the leading entry of the first row. So matrix B is in reduced row-echelon form. How about matrix C? Matrix C, it does not have any 0 row, so condition 1 is met. The second condition, for each non-zero row, the leading entry is 1, and all the other entries in the column is 0. So second condition is met. However, the third condition is that the leading entry in each row is to the right of the leading entry in any row above it. But the leading entry in the second row is to the left of the leading entry of the first row. So matrix C is not in reduced row-echelon form. How about matrix D? It does have a 0 row. However, this is not at the bottom of the matrix. So matrix D, the first condition already fell. It is not in reduced row-echelon form. And lastly, matrix E. It has a 0 row and it is at the bottom of the matrix. So first condition is met. Second condition, for each non-zero row, the leading entry is 1. This is also met. On top of that, all other entries in the column of leading entry are 0. This is also met. And the third condition, the leading entry in each row is to the right of the leading entry in any row above it. This condition is also met. So matrix E is in reduced row-echelon form. Now let's look at this example. Let's use the 3 elementary row operations to reduce this matrix into reduced row-echelon form. Since we want the leading entries appears from top left to bottom right. Furthermore, we want the leading entry to be 1. So I can do row 2 is replaced by a third of itself. Then I'm going to exchange row 1 with row 2. So the matrix becomes 1, -2, -1, and 0. Then 0, 0, 1, 2. and the third row remains the same. 6, -12, 2, and 11. Now I have my first leading term in the first column, but I also want to make all the other entries in this column to be 0. So I will want to eliminate this 6. So I'm going to replace row 3 by row 3 minus 6 times row 1. Then this matrix becomes 1, -2, -1, 0, 0, 0, 1, 2. The first two rows remain the same, and the third row is 0. Then -12 minus 6 times -2, that is also 0. Then 2 minus 6 times -1, that is 8. And the last entry is 11 minus 6 times 0, so that is 11. Now I have the first leading term in the first column, and all the other entries in the first column are 0. Now let's look for the second leading entry. In the second row, I have a leading entry of 1 in the third column, but I would like to make the other entries in the third column to be 0. So I want to eliminate the -1 and the 8. To do that, I can replace row 1 by row 1 plus row 2, and row 3 is replaced by row 3 minus 8 times row 2. Then the matrix becomes 1, -2, 0, and the last entry is 0 plus 2, which is 2. And the second row remains the same, 0, 0, 1, and 2. And the third row is now the third row minus 8 times the second row. The first two does not change, and the third entry is 0, and the last one is 11 minus 8 times 2. So 11 minus 16, that is -5. So now we have the first two leading terms are 1s, and in the same column, all the other entries are 0. Now moving on to the third row. The leading entry is this -5, but we want to make the -5 into 1. So I'm going to replace row 3 by -1/5 of itself. Then I will also want to eliminate the 2's in the same column. So after I replace row 3 by -1/5 of row 3, I will also like to replace row 1 by row 1 minus 2 times row 3, and row 2 is replaced by row 2 minus 2 times row 3. Then I get 1, -2, 0, 0, and 0, 0, 1, 0, and 0, 0, 0, 1. So just a final check whether this is in reduced row-echelon form. In the first row, we have the first leading term, that is 1. In the first column, all the other entries are 0. So that is good. Now moving on to the second row. We have the leading term in the third column, which is to the right of the first leading entry. So this is also good. In the same column, all the other entries are 0. Then moving on to the third row. The leading entry is also 1, and the entry is on the fourth column, which is on the right of the first two leading entries. And in the same column, all the other entries are 0. So yes, this is in reduced row-echelon form. The reason why we will want to reduce a matrix is that can easily help us to solve for a system. Let's look at this example. Here I have a system of 3 equations with 2 unknowns. In my previous video, I already mentioned that we can write a system into an augmented matrix form. So I'm going to rewrite this as 2, 3, vertical bar, -1. That is the first row of my matrix. Second row is 2, 1, and 5. And third row is 1, 1, and 1. So the goal is to reduce the coefficient matrix on the left into reduced row echelon form. So we want leading entries of 1. So I'm going to exchange row 1 with row 3. Then the matrix becomes 1, 1, and 1. Second row remains the same, 2, 1, and 5, and 2, 3, and negative 1. Now I have my first leading term, it's 1. Then I want to eliminate the 2 below the 1. So I'm going to replace row 2 by row 2 minus 2 times row 1. And row 3 is replaced by row 3 minus 2 times row 1. Then the matrix becomes 1, 1, and 1. First row remains the same. Second row is now 0 and 1 minus 2 times 1. That is negative 1. And on the right is 5 minus 2 times 1. So that is 3. Third row is 0 and then 3 minus 2 times 1. That is 1. And negative 1 minus 2 times 1. That is negative 3. So now I have my first leading entry. And in the same column, all the other entries are 0. Now in the second row, the leading entry is negative 1. So I want to make it into 1. To do that, I can do row 2 is replaced by negative of row 2. Furthermore, I would like to eliminate the 1. So I'm going to replace row 1 by row 1 minus row 2, and row 3 is replaced by row 3 minus row 2. So the second row is now 0, 1, and negative 3. First row is now row 1 minus the second row. That is 1, 0, and 1 minus negative 3. That is 4. The third row is now row 3 minus row 2. And we get 0, 0, and 0. And remember that in matrix form, the columns represent the variables. The first column is for x, the second column is for y. So the first row tells us that x plus 0y equals to 4. Second row tells us 0x plus y equals to negative 3. And the third row is 0x plus 0y equals to 0. So now we get the solution. Solution is x equals to 4 and y equals to negative 3. So that is how by reducing a matrix can help us to solve a system. And that is the end of the video. If you have any questions, feel free to comment below. If you like my videos, please like and subscribe, and I'll see you in the next video.